Assalamu alaikum students. Now we will solve a numerical problem related to voltage regulation and efficiency of a transformer. To understand all the concepts related to voltage regulation and efficiency in much better fashion. So this is the last lecture of this course. So first of all, we will discuss the given data. The first one is the rated apparent power is basically given here 15 kVA. It means in this particular problem, we are using a transformer whose rated apparent power is 15 kVA. And the voltage ratio of the given transformer is 2300 divided by 230 volt. It means, as we know, voltage ratio is equal to primary voltage divided by the secondary voltage. It means primary voltage is basically equal to 2300 volt. So Vp is equal to 2300 volt and the secondary voltage is equal to 230 volt. The value of the secondary voltage is 230 volt. By comparing these two voltages, as you can see in these two voltages, primary voltage is greater than the secondary voltage. So we can say that the primary voltage is basically greater than the secondary voltage. It means of the primary side of the given transformer is the high voltage side and the secondary side of the given transformer is the low voltage side, because the voltage across the primary circuit of the given transformer is 2300 volt and the secondary circuit is 230 volt. So this is the high voltage side and this is the low voltage side. The other parameters are open circuit test parameter is given here. Open circuit voltage is equal to 2300 volt. Open circuit current is equal to 0.21 ampere. Open circuit power is basically equal to 50 watt. And the short circuit test parameter is given here. V short circuit is equal to 47 volt. I short circuit is equal to 6 ampere and P short circuit is equal to 160 watt. As we have already discussed, by performing open circuit test, we basically calculate the core losses of the transformer. And by performing the short circuit test, we basically calculate the copper losses of the given transformer. So this is the core losses of the transformer and this is the copper losses of the transformer. So these data is basically given after performing the open circuit test and the short circuit test of the transformer. The connections diagram of the open circuit test and the short circuit test is shown here. So this is the open circuit connection diagram, because the data have been taken by using the connections shown here. The data after performing the open circuit test, this is the connection diagram of the open circuit test and this is the connection diagram of the short circuit test. As we have already discussed, in case of open circuit, the secondary side of the transformer will be open, and in case of short circuit test, the secondary side of the transformer will be short circuited. So we will calculate the power, short circuit voltage and short circuit current in the primary side of the transformer. And similarly, we will calculate the open circuit power, open circuit voltage and open circuit current in the secondary primary side of the transformer. In case of open circuit, we will open the secondary side and in case of short circuit, we will short the secondary side. So these are the given information, given data in this numerical problem. So now we will discuss the question which we will answer in this numerical problem. So this is the approximate equivalent circuit of the transformer referred to the primary side of the transformer, because the high voltage side in this particular problem is the primary side. We can calculate from the voltage ratio because the primary voltage is greater than the secondary voltage. It means the high voltage side is the primary side and low voltage side is the secondary side. So this is the approximate equivalent circuit referred to the high voltage side of the transformer or the primary side of the transformer. So part 1 of this particular problem is, in part 1 we will find the equivalent circuit. So this is the equivalent circuit referred to the high voltage side. High voltage side means referred to the primary side of the transformer. So in case of equivalent circuit, first of all we will find these 4 parameters, that is RC, XM, R equivalent and X equivalent. Then we will put these 4 parameter values in this circuit. So this is the part 1 of the given numerical. So first of all we will calculate the value of RC and XM, then we will find the R equivalent and X equivalent. As we have already discussed, the value of RC and XM we can calculate by performing the open circuit test of the transformer, and we can calculate the values of R equivalent and X equivalent by performing the short circuit test of the transformer. So first of all we will solve the part A of this numerical problem. The part A is basically find the equivalent circuit of this transformer referred to the high voltage side or the primary side of the transformer. So first of all we will perform the open circuit test. The result of the open circuit test, as we have already given in the given data of the given numerical problem. So first of all we will determine the values of RC and XM, that is excitation branch elements. As we know, cos theta in open circuit is equal to power open circuit divided by voltage open circuit into current open circuit, and the theta will be equal to cos inverse P over V into I. Putting the value of P, V and I in this equation, we will get the value of the P in this particular problem is given here 230 volt. So the value of the power is missing, given problem is here 50 watt. So the power of open circuit is given 50 watt. The value of the voltage is 230 volt and the value of the current is 2.1 ampere. After solving this equation, open circuit theta will be equal to, that is theta open circuit will be equal to 84 degree. So this is the open circuit angle, that is theta open circuit is equal to 84 degree. So now we will find the excitation admittance, that is, as we know, admittance is basically equal to open circuit current divided by the open circuit voltage angle of minus theta, because in case of transformer current is basically lags the voltage. When the current will lag, then the angle of the current will be in minus. Admittance is also equal to 1 over RC minus J 1 over XM. So our main objective by performing the open circuit test is to calculate the values of RC and XM. So putting the value of open circuit current and open circuit voltage and the value of theta in this equation, we get the value of the current is 0.21 and the value of the open circuit voltage is basically 230 volt. And the value of the angle of the theta is basically given here, as we have already calculated. Theta is equal to 84 degree. So the value of the So the value of the theta is 84 degree. So this is the polar form. We can convert this polar form into rectangular form. So this is the rectangular form of the given polar form. I just convert the polar form into rectangular form is equal to 1 over RC minus J 1 over XM. So to find the value of RC and 1 over XM, we just compare these two equations. We will compare real part with the real part and the imaginary part with the imaginary part. The real part is basically 1 over RC is equal to, this is the real part of this equation, and this is the imaginary part. So real part 1 over RC will be equal to 0.00095, and the imaginary part 1 over XM is equal to 0.0000908. Now, after the cross multiplication, we can find the value of RC and XM. The value of the RC is basically equal to 1 over 0.000095. After solving this equation, the value of RC is basically 1050 ohm. So this value of the RC is referred to the secondary side of the transformer. The reason is that the value of this RC is basically referred to the secondary side because we perform, as we have already discussed, we perform the open circuit test of the transformer in the low voltage side. So in the given problem, the low voltage side is the secondary side. So that's why RC secondary is basically equal to 1050 ohm. After solving this equation, we get X magnetization reactance in the secondary side is equal to 110 ohm. So these are the excitation branch elements referred to the secondary side. The reason is that because we perform the open circuit test in the low voltage side of the transformer. So by performing the open circuit test, we calculated the value of RC and XM. Now we will perform the short circuit test to calculate the value of R equivalent and X equivalent. As we have already discussed, we perform the short circuit test to determine the values of R equivalent and JX equivalent. So first of all, we will calculate short circuit angle. As we know, short circuit theta will be equal to cos inverse P over V into I. Putting the value of P short circuit, V short circuit and I short circuit in this equation, we get the value of the P short circuit is given in this numerical problem is 160 watt. The value of the voltage is 47 volt and the value of the current is 6 ampere. So after solving this equation, we get the short circuit theta is equal to 55.4 degree. So this is the angle of this is the short circuit angle. Now we will calculate the value of R equivalent and X equivalent. As we know, short circuit impedance is equal to V over I angle of theta. Now the angle of theta is positive. The reason is that the angle of the current in case of transformer is the angle of the current is negative. When we will take the angle of current from denominator to numerator, then the angle will be positive, is equal to R equivalent plus JX equivalent. So first of all, we will put the value of V and I and theta in this equation. The value of the short circuit voltage is 47 volt. The value of the short circuit current is 6 ampere and the value of the theta is 55.4 degree. This is the polar form of this equation. So first of all, we will convert this polar form into rectangular form. Then we will compare real part with the real part and imaginary part with the imaginary part. So the rectangular form of the given polar form is 47 over 6 angle of 55.4 degree is equal to, in rectangular form, 4.45 plus j 6.45 is equal to R equivalent plus jx equivalent. Now we will compare real part with the real part and imaginary part with the imaginary part. So the value of R equivalent will be 4.45 and the value of x equivalent will be 6.45. So these values are referred to the primary side. The reason is that we perform the short circuit test in the high voltage side of the transformer. As we know, in the given transformer in this numerical problem is the high voltage side is primary side and the low voltage side is the secondary side. As we know, we perform the short circuit test in the high voltage side of the transformer. So that's why R equivalent and X equivalent will be in the primary side of the transformer, because the primary side is the high voltage side of the given transformer. So now we will draw the high voltage side equivalent circuit. So now we will draw the equivalent circuit referred to the high voltage side or the primary side of the transformer. The equivalent circuit with referred to the high voltage side of or primary side of the given transformer is shown here. This is the excitation branch and this is the series impedances. So as we have already find the value of RC and XM with respect to secondary side of the transformer. And as we know, we will draw the circuit referred to the high voltage side or primary side of the transformer. It means, first of all, we will convert the value of RC and XM from secondary to primary. As we know, RC primary will be equal to A square into RC secondary. As we have already calculated, the value of RC secondary is 1050 and the value of turn ratio, that is Vp over Vs, is equal to 10. So after multiplication we get the value of RC with respect to the primary side is equal to 105 kilo ohm. Similarly, so this is the value of magnetizing reactance referred to the primary side. Putting the value of RC, XM, R equivalent and X equivalent in this equivalent circuit. So this is the high voltage side equivalent circuit. The value of RC is 105 kilo ohm. The value of magnetizing reactance is 11 kilo ohm. The value of equivalent resistance is 4.45 ohm and the value of equivalent reactance is 6.45 ohm. So this is the part A of this numerical. Now we will solve the part B of this numerical. The part B of this numerical is find the equivalent circuit of this transformer referred to the low voltage side. In part A, we find the equivalent circuit referred to the high voltage side. In part B is basically we will draw the equivalent circuit of the transformer in part A referred to the low voltage side. As we know, the turn ratio is basically given here. A is equal to NP over NS is equal to VP over VS is equal to 10. So first of all, we will convert the primary elements as we have already calculated in the part A. First of all, we will convert the secondary reactances and primary reactances into secondary side of the transformer, because the low voltage side of the given transformer is the secondary side. It means, first of all, we will convert all the resistances and reactances into the secondary side of the transformer. So R equivalent secondary will be equal to R equivalent primary divided by A square. R equivalent primary is basically given here 4.45 divided by 10 square will be equal to 0.0445, and X equivalent secondary will be equal to X equivalent primary divided by A square. Putting the value of X equivalent primary is equal to 6.45 divided by the value of A is 10, and A square means 10 square. After solving this relationship, then the final answer is 0.0645 ohm. Now we will convert the RC primary into secondary. That is, RC secondary will be equal to RC primary divided by A square. Putting the value of RC primary and A in this equation, we get the value of RC primary is 105K and the value of A is A square, 10 squares. After solving this, we get the value of RC secondary will be equal to 1050 ohm. Similarly, we will find the magnetizing reactance in secondary. First of all, we will put the value of magnetizing reactance primary in this equation. The value of magnetizing reactance referred to the primary side is 11K and the value of A square is 10 square. After solving this, we get the value of magnetizing reactance referred to the secondary side is equal to 110 ohm. So the equivalent circuit referred to the low voltage of the given transformer is shown here. Now the low voltage side is basically the secondary side. This is the equivalent circuit of the given transformer referred to the secondary side of the transformer or low voltage side of the transformer. Now the value of RC over A square, as we have already calculated, is 1050 ohm. The value of XM over A square is equal to 110 ohm. The value of R equivalent is 0.0445 ohm. The value of X equivalent is 0.064 ohm. So this is the equivalent circuit of the given transformer referred to the secondary side or low voltage side of the transformer. Now we will solve the part C of this numerical problem. The part C of the given numerical problem is calculate the full load voltage regulation at 0.8 lagging power factor, unity power factor and at 0.8 leading power factor. So as we know, the full load current on the secondary side is IS rated is equal to apparent power rated divided by secondary voltage rated. Putting the value of S and rated and V secondary rated in this equation, we get the value of apparent rated power is given in this numerical problem is equal to 15 kVA. And the rated voltage is given, secondary rated voltage is given in this numerical problem, Vs is equal to 230 volt. After solving this, we get the magnitude of rated secondary current is equal to 65.2 ampere. Now, our main objective is to calculate the voltage regulation in part C. To calculate the voltage regulation, as we know, voltage regulation is equal to no load secondary voltage, Vs no load or Vp over A minus full load secondary voltage divided by full load secondary voltage multiplied by 100. So our main objective is to calculate the voltage regulation at 0.8 lagging power factor, unity power factor and at 0.8 leading power factor. So this is the formula of the voltage regulation. So first of all, we will find the voltage regulation at 0.8 lagging power factor. So as we know, in case of lagging power factor, theta will be equal to cos inverse 0.8 as given. Cos theta is equal to 0.8 lagging. So theta will be equal to cos inverse 0.8. After solving this, we get the angle is basically theta is equal to minus 36.9 degree. Minus is basically shows that the power factor is lagging. As we know, in case of lagging power factor, it means the load is inductive. When the load will be inductive, then the current will lag. When the current will lag, it means the angle of the current will be less than the angle of the voltage. If the angle of the voltage is 0 degree, then the angle of the current will be in minus. So the secondary current will be equal to, this is the magnitude 65.2 as we have already calculated, and this is the angle due to lagging power factor, that is minus 36.9 degree. So this is the secondary current in case of lagging 0.8 lagging power factor. In case of leading power factor or unity power factor, the angle of the current will change, magnitude will remain same. So therefore, now first of all we will find the no load secondary voltage. The full load secondary voltage is basically given here 230 volt. So first of all we will calculate the no load secondary voltage. So that is Vp over A. As we know, Vp over A is equal to Vs plus R equivalent into Is plus Jx equivalent into Is. Putting the value of Vs, R equivalent, Is, X equivalent, Is in this equation, and J means 90 degree. We will put J is equal to 1 angle of 90 degree. As we know, the value of J is 1 angle of 90 degree. After solving this equation, we get the value of Vp over A is equal to 234.85 angle of 0.40 degree volt. So this is the no load voltage at 0.8 lagging power factor. So overall voltage regulation will be, so putting the value of Vp over A and Vs full load is equal to 230 volt in this equation, we get voltage regulation is equal to the value of Vp over A is basically 234.85 and the value of the secondary voltage at full load is basically given here 230 volt divided by 230 multiplied by 100. Then the voltage regulation will be equal to 2.1%. This voltage regulation is the positive voltage regulation. Positive means when we will connect the load across the secondary side of the transformer, then the voltage will drop. Now as you can see in this equation, no load voltage is basically greater than the full load voltage. So that's why the voltage regulation is positive. Now we will find the voltage regulation at unity power factor. So as we know, in case of unity power factor, cos theta is equal to 1. The value of the theta will be 0 degree. That theta is equal to cos inverse 1. The answer is 0 degree. Therefore, the secondary current will be equal to now 65.2 angle of 0 degree. And similarly, as we know, Vp over A is equal to Vs plus R equivalent Is plus Jx equivalent Is. Putting the value of Vs, R equivalent Is, Jx equivalent Is in this equation, we get 230 angle of 0 degree as given. The value of the voltage is 230 angle of 0 degree and the value of the R equivalent is 0.0445. Value of the current is now 65.2 ampere. The angle is basically 0 degree. The reason is that the power factor is unity power factor. Now after solving this, we get the value of Vp over A is equal to 232.94 angle of 1.04 degree volt. Now, this is the no load secondary voltage. Similarly, we will find the voltage regulation VR is equal to Vp over A minus Vs full load divided by Vs full load into 100. Putting the value of Vp over A, Vs full load and Vs full load in this equation, we get the value of Vp over A is 232.94 minus the value of the secondary voltage at full load is given here to 30 volt divided by 230 into 100. After solving this, the value of the voltage regulation is now 1.28%. Voltage regulation is still positive. The reason is that in case of resistive load, when we connect the resistive load, the voltage will drop as well. Now, as you can see in this equation, the no load voltage is greater than the full load voltage. So that's why the voltage regulation is positive. So now we will find the voltage regulation at 0.8 leading power factor. As we know, in case of 0.8 leading power factor, the angle of the current will be positive. Is given here cos theta is equal to 0.8. Theta will be cos inverse 0.8. Now we will take the angle of theta will be positive. The reason is that now the power factor is leading. When the power factor will be leading, then the current will be leading. So in this case, current will be leading. It means the angle of the current will be greater than the angle of the voltage. If the angle of the voltage is 0 degree, then the angle of the current will be positive. So that's why the angle of the current is now positive. Similarly, we will find the value of Vp over A by using this equation, putting the value of Vs, R equivalent Is, J, X equivalent Is in this equation, we get 230 angle of 0 degree, 0.0445, 65.2 angle of 36.9 plus J 0.0645 into 65.2 angle of 36.9 degree. After solving this equation, the value of the Vp over A is now 229.85 angle of 1.27 degree volt. Now the no load voltage is 229.85. The voltage regulation will be Vp over A minus Vs full load divided by Vs full load into 100. Putting the value of Vp over A, Vs full load in this equation, we get 229.85 minus 230 divided by 230 multiplied by 100. After solving this, voltage regulation is equal to minus 0.062%. Now the voltage regulation is negative. Negative voltage regulation means when we connect the load, then the voltage will increase. So now as you can see in this equation, full load voltage is greater than the no load voltage because now the load is capacitive load. In case of capacitive load, the voltage regulation will be negative. So this is the part C of the given problem. We can draw the phasor diagram as well, as we have already discussed. So in part C, we will draw the phasor diagram at 0.8 leading power factor, 0.8 lagging power factor, and at unity power factor. The phasor diagram, as we have already discussed in detail, how will we draw the phasor diagram? So this is the part C of this numerical. Now we will solve the last part of this numerical. Part D of this numerical is basically same as part C. So part D is basically same as part C. So part D will be your homework. Now we will solve the part E of this numerical problem. This is the last part. Part E is basically what is the efficiency of the transformer at full load. with a power factor of 0.8 lagging. So in this part we will find the efficiency of the transformer at 0.8 lagging power factor. As we have already discussed, in case of efficiency, first of all we will calculate the losses of the transformer. As we know, the copper losses, the formula of the copper losses is equal to I square into R equivalent. Putting the value of IS and R equivalent in this equation, we get the value of IS is 65.2 ampere and the value of R equivalent is 0.0445. After solving this, the answer is 189 watt. So the copper losses of the given transformer is 189 watt. Now we will find the core losses of the given transformer. The formula of the core losses is Vp over A square over RC. Putting the value of Vp over A. Now the power factor is 0.8 lagging. As we have already calculated the value of Vp over A at 0.8 lagging power factor. So the value was Vp over A is 234.85 square divided by the value of RC is 1050. After solving this, we get the answer is 52.5 watts. So this is the copper losses of the given transformer. Now we will find the output power. As we know, the output power is Vs Is cos theta. Putting the value of Vs Is and power factor in this equation, the value of the Vs is 230 volt, the value of the current is 65.2 ampere and the power factor is 0.8 lagging. It means the theta will be cos 36.9 or simply cos theta is equal to 0.8. Cos 36.9 means 0.8. That is 0.8 power factor lagging. After solving this, the answer, the output power is equal to 12,000 watt. So this is the output power of the given transformer. Now the efficiency of the given transformer is VSIS cos theta over copper losses, core losses plus output power. Putting the value of output power, copper losses, core losses in this equation, we get the value of the output power is 12,000 watt. The copper losses is 189 watt. Core losses is basically 52.5 watt plus the output power is 12,000. After solving this, the efficiency is basically equal to 98.03%. So this is the efficiency of the given transformer, that is 98.03%. So the numerical is complete. Now we will discuss the autotransformer. Autotransformer is basically used to change the voltage levels by only a small amount. That is, autotransformer is basically a transformer is used to change the voltage level by only a small amount. For example, if we want to increase a voltage from 110 volt to 120 volt, that is just 10 volt, or from 13.2 kilovolt to 13.8 kilovolt, only small voltage if we want to increase, then we will use the autotransformer. So now the question is, why do we use autotransformer? Autotransformer is basically used to compensate the voltage drops in a power system, that is particular in transmission lines. When we transfer the electricity over long distances through transmission line, voltage drops occurs. So to compensate the voltage drop, we use autotransformer. It is not conventional transformer. The conventional transformer is basically, in conventional transformer there are two windings, that's a primary circuit and the secondary circuit. So instead of conventional transformer, To compensate the voltage drops in a power system, particularly in a transmission lines, we use autotransformer. Now we will discuss the diagram of the autotransformer. The diagram of the conventional transformer, as we have already discussed a lot of time, this is the secondary side of the conventional transformer, this is the primary side of the conventional transformer. This is the secondary voltage, secondary current, and this is the secondary number of turns. This is the primary voltage, primary current, and this is the primary number of turns. This is the diagram of the conventional transformer. Normally we use conventional transformer. And this is the diagram of the autotransformer. In case of autotransformer, we connect the primary winding and the secondary winding in series with the primary winding. Now as you can see in this diagram, we connect the secondary winding in series with the primary winding. This is the primary winding and this is the secondary winding. We just connect, in case of autotransformer, secondary winding in series with the primary winding. So undotted point of the secondary will connect the dotted point of the primary point. So that's why this is called the additive manner. In additive manner, we connect the undotted point of the secondary with the series with the dotted point with the primary side. So this is the autotransformer diagram. This is the conventional transformer. So if we want to increase or the voltage or decrease the voltage by just a very small amount, then we use autotransformer. So if we use the conventional transformer, then the conventional transformer is very expensive because there are two windings, two circuits, secondary circuit and primary circuit. Here is only one circuit. So this is the diagram of the autotransformer. This is the high voltage side of the autotransformer because here the more number of turns, and this is the low voltage side of the autotransformer because input is connected with less number of turns. And here the secondary side is high voltage side and the primary is low voltage side. So that's why this is the step up autotransformer. The diagram of step down autotransformer is shown here. In step down autotransformer, we connect the primary side with more number of turns and we will take the output voltage with less number of turns. So this is the diagram of step down autotransformer. This is the diagram of step up autotransformer. And here the high voltage side, IH current will be equal to IL will be equal to ISC, that is series current, and IL will be equal to IC. IC means common winding, which is using low voltage side and the high voltage side as well. This is the common winding and this is the series winding. SC means series. H means high, L means low voltage side. NC means common number of turns, IC means common current. So the IL will be equal to IC plus ISC. Similarly here, VH will be equal to VC plus VSC. And VL will be equal to VC. Low voltage side is basically connected with a less number of turns, that is VC. And IH will be equal to ISC. So the turn ratio will now be equal to VP. This is the primary is VL, secondary is the VH. VL over VH is equal to primary number of turns is basically NC and secondary number of turns is basically the sum, NSC plus NC. So NC over NSE plus NC. So this is the voltage ratio formula in autotransformer. And this is the current ratio formula in autotransformer. As we know, in case of current ratio, current and voltage are inversely proportional. So in case of current, IL over IH will be equal to NSC plus NC divided by NC. So this is the basic concept of autotransformer. Now the course is complete. So that's it for this subject lectures.